not an expert in random matrix theory, okay? What I'm doing right now is mainly analyzing brain data. So I will give you a couple of observations of what happens or can happen when you start playing with results from random matrix theory applied to neural time series. First, that's not the last slide, that's the first one. So actually, I wanted to briefly introduce you to the whole areas of neuroscience studies, and well, what type of questions maybe people pose them in that field. Of course, first you wanna get to know a person and find out what his or her characteristics are. Then you wanna try to get the idea of what type of person that is, then try to predict his or her behavior, and then you want to control that person. So let's help neuroscientists do that. Well, they usually look at in clinical studies especially, they look at differences between groups of people. So usually healthy and diseased or disordered, psychologically disordered people. They, if they're not the clinical studies, there are all those neurocognitive psychologists that are interested in how some information is processed by our brains. What all the things mentioned here: memory, language, some conflicting information, your emotional states, what kind of representations they have in your head. The interesting questions are in which places of your brain some things are represented or where they happen, at what time, depending relative to the stimulus, to what you see or hear or whatever external input you have. What is the order of processing information? What are the pathways? And yeah, generally those are the questions that you probably always see somewhere in this type of literature. On the other hand, what physicists might ask, or maybe also mathematicians as well, is your brain critical? Is it like on a border of phase transitions, maybe, if you're actually interested in phase transitions and condensed matter and so on. Are there some attractor dynamics of your brain? Are there some stable or unstable states in your brain? Is it in what way is it a self-organized structure? And so on and so on. So just put down of your favorite question here, and then try to get the neural data and deal with it. So to try to tackle with those questions, we have a couple of options in terms of what we want to measure. And I'm not going to go into neurobiology, like those low-level neural dynamics, but rather on to what neuropsychologists would take. So all those things that would put around your head. So, but before that, it's in clinical and neurocognitive studies. It's not the only thing. It's not just that you'll have your neural data. You'll have, first of all, the questionnaires that all of you hate and probably you think it's just worthless. Still, that's some type of data. You'll have all the behavioral measures, which are whatever a person during an experiment will click or tell, or however he or she will respond. Then you have other physiological data, heart rate being one, then movements, maybe actually hormone concentration, whatever there can be. So just to show you that that's well, of course there's a big picture. I mean, I'm a whole person, I'm not just my brain. So whatever conclusions you might have from the neural data, it's good to have a setting where you then associate it with all the other things there. So going to something I will not talk about, you can do, for example, electrocorticography, which is invasive. That is, those electrodes really sit on your brain, like open head. So, which is good because you have all those local field potentials, electrical activity, not insulated by your bones and so on. So you get a good quality data, but of course you do that only in clinically clinical patients that just need some brain operation. So we don't do that. This person is smiling, so this does not have. This is the electroencephalography. So all those electrodes here are put on the scalp, on the skin of your head. So it's good that you can. It's cheap. You can do it with anybody. The problems are the signal is not as good quality. You don't really get exactly neural activity. It's very mixed because of how your brain is folded. You can can have signal from somewhere here that ends up in an electrode on the other end of your head. So all those sources are mixed. You have to, or you might try to entangle them. You might try to localize them inside your head. It's all complicated and not that easy actually.
Can you try the both method to calibrate the second somehow?
To some extent. So there are dual fMRI and EEG equipments. I'm not sure if you can do electrocorticography and EEG because your head is open already. So
I know.
Yeah. And just to show you what type of time scales we have here. So the typical recording would take several minutes or even a couple of hours. You can take your whole sleep recording, so like 8 hours maybe, with a very good temporal resolution. And while whatever happens with your neurons is basically like 1 millisecond after your neuron fires, it needs at least 1 millisecond to get back into normal state. And then the time that it takes to travel on the axons and so on. So having this type of sampling is the right choice, we say. On the other hand, you have the spatial scales, and those are not as optimistic because you can, but in clinical setting, you can just have even one electrode actually to measure, if you're epileptic or not. That's actually enough. But you have also more than that. But again, it's all mixed, and there's really plenty of neurons under that electrode. So it's it's really large-scale information that we get from that technique. And EEG is the thing that I'm going to show you later. The data that we're analyzing. With the other option that we're also playing with, but I'm not going to show it to you today, is the functional magnetic resonance. So this thing is gives you much better quality in terms of the spatial scales because you've got all those voxels which are 3 by 3, actually 27 to the millimeter squared. So 3 by 3 by 3 millimeters. So we've got thousands of voxels. Each of those voxels gives you one time series. Okay. But on the other hand, the temporal resolution that you get is really low. It's in the equipment that we have in Krakow, it's basically 1.8 seconds, I guess, for one sample of the time source. Yeah. And what is worse, it's not direct neural activity, it's the oxygenation of your blood. Okay, so it's indirect inference that we have, that we think that, okay, after your neurons have fired, they need some energy to replenish their resources, and then your vein, your blood starts flowing with the oxygen to those places that did the job, and it takes quite a lot of time actually. So if you're okay, so again, this is the type of signal that you'd get. There's some motor areas left and right, which are very nicely correlated. That's the thing that you get when you start calculating the correlation matrices. So it seems that it looks much nicer than EEG, which can get any type of noise inside here. Yeah, people know that all the correlations that you have in your brain can depend on your conscious state, on the type of task that you're doing, and so on and so on. Now, if you think about how to approach it from the randomatics theory perspective, you do remember that if you take a Pearson correlation estimator and in the infinite limit of the time and number of channels, the distribution of the spectral distribution depends on the rectangularity. So you might think that it's better to take EEG because it has better time resolution, so you get plenty of time points and just a couple of channels. And it's much worse for the fMRI. I mean, the spectrum would be very broad because of just the number of channels. You could just actually get a lot of zero eigenvalues as well. So we go to the EEG basically, but what is it only correlation matrices? Not necessarily. Well, people do mutual information between each channel. Quite often, people are interested in the polysynchronization phenomena, just because we know that, especially in EEG, you've got the brain rhythms, like this alpha, beta, theta, and so on. So some parts of your brain are supposed to be oscillators, and then you can measure the instantaneous phase of that oscillation, and you measure it if different places of your brain are synchronized, for example. And I think people, well, of course, the next thing after you get a matrix, you try to decompose it. That's what we do, into diagonalized. And just to give you a brief idea of what people have done until now. But I think one of the first actually people that have been doing something with quantum matrix theory and the brain was Professor Frost. Which actually they were using magnetoencephalography, so yet another one type of measurement. And they got more or less something which was looking like GOE ensemble. They also actually used the time-lapse correlations already. So I think they were able to find the time lag between hemispheres with some in some auditory response tests. Quite a lot of people actually try to do something with epilepsy, which was mentioned just the talk earlier, I guess. But it's a very hard topic. I mean, detecting at which point there is going to be an onset of epileptic seizure. So people have tried many things there, among others the random access theory thing. But I mean, usually the thing that people look at is just, okay, does the eigenspectrum look like what we expect from the theory for Gaussian random variables or all the other classical measures? And it's hard to get beyond that, actually. In our case, okay, we're going to use EEG in several setups. So one thing is, so now that's a way you can do experiments. You can ask a person to do some task for you, to respond to some stimulus, or you can ask a person to just do nothing. So that's what's called resting state. It's actually been introduced not that long ago, because people thought that you just get garbage. But actually what you get from the spontaneous activity of your brain is also something that you would see in the task, but it's just not temporally structured, connected to any stimulus. It just appears and disappears, but the correlations as with the task are there. So that's one of the things that happened in our experiments. Another thing was a task which I might just calculated. So we had a EEG with 65 channels, this sampling rate, which is enough to get anything you want from EEG data, and a couple of minutes of recording from each subject. I'm just going to show you just one subject. So there's like exploratory. We're just trying to find out whatever we can see interesting there. Yeah.
What's flanker?
Flanker. So that's the type of task that you do, which is basically, in our case, that was a couple of arrows shown on the screen. One of the arrows in the middle could be aligned with the others, or could go in the opposite direction. And the task of the person was to choose if the alignment is correct or incorrect. So it's kind of like, you get conflicting information, you have to do this very fast, you can make mistakes. That's the important thing is actually what you do next. That is, you get the raw data. Of course, whatever raw data you get, it's not going to be good. You have to massage it, you have to do something with it. But in our case, actually, I just did the simple filtering, and then I left everything else as it were, actually just to see whatever result, effect it will have on the things we will measure with the eigenvector and so on. So, the question is, okay, will you see a channel, well, like an electrode that's not sticking to your head? Will you see that in your eigenspectrum? Will you see, people blinking or doing things that you ask them not to do, and so on and so on. Now, getting more in detail into the data. So, if you want to compare whatever measure from random matrix theory with the data, you assume that you want to compare it with a Gaussian stationary processes. The point is, this thing is, of course, it's non-stationary. I mean, we're doing many things. We're thinking about many things. We're not even aware of. So that's just a couple of examples. That's the perfect case where you would see, so the signal is already standardized. So you assume that it's going to have standard deviation of 1 for let's say for the activity. The other one, the blue ones are the increments, which is we're just making a derivative of the time series just to make it more stationary. But you can see that anything can happen. They're not going to be on that line. So we have a surely non-stationary process, and that's for a good reason as well, because the spectrum of it is more or less 1 over f to the power more or less 1 or 2. It depends. It can depend on the person. Can depend on, you know, if the person has disease, actually, whatever. So that's a general thing that you see, that there is a 1 over f spectrum with some peaks that may correspond to all those algorithms or the electricity that came into your equipment. So that's going to be non-stationary. It's not really Gaussian, unless you, after differentiation, it looks somewhat Gaussian. But anyway, you get something that is, so the red line here is the Gaussian with the logarithmic scale. So you're not going to get anything that you expect to be as the reference one. Yeah? And then you get all those. Okay, so this type of non-stationarity, but also the non-stationarity that psychologists don't want to have. So here you can see that somebody blinked, and then probably he or she moved during the recording within just 2 seconds, and of course that's gonna spoil your inference later on. Now, what we can do with all that. Okay, so first, well, we're gonna look basically on equal time correlations and lagged correlations. Here's the lag. So in equal time correlations, you basically know everything about that. With the lagged correlations, the one thing is you have a couple of time series, a couple of channels with the time, another couple of and the same channels with time, and you shift all of them in time. Okay, so it's all your data against all your data shifted. The sad information is you don't have any knowledge if something would come better or worse if you shifted just individual channels, which actually might be more interesting. What you do see if you just start looking, just look at the largest eigenvalues. Simple thing. And that axis is time in a second, so that's a couple of minutes. You're going to see that there are large jumps in the first eigenvalue, the second, the third. More than that, you can look at the distribution of the values of the eigenvectors. So that's the first eigenvector and the second, third. And you can see that some of those jumps in the eigenvalues actually are connected to jumps in the eigenvectors. Some are not. So like this 8 here, there's going to be a jump here, but no jump in some eigenvectors. Now, this is just showing you pictures basically. Okay, this is the raw time series. This time series after differentiation. Okay, so supposedly more stationary and it looks nicer. What you can see that there are a couple of events here numbered, but they differ. In terms of did that event appear here, or in both cases, or did it appear in eigenvalue or in eigenvector or in both? You already have a couple of possibilities, and actually different events can appear in different places. And some of the, and they're actually different type of, in this case, actually they're artifacts. So what you get from those jobs is the collective behavior of your brain. If you move during the experiment, that's totally collective behavior because you move all the channels all, at the same time. So that's not necessarily very informative if you did the pre-processing right and you get rid of all the artifacts, but it's not also the case that well, the artifact removal algorithms can be improved, and maybe that information is actually one way of doing that. This is to say that until now, I guess most of the artifact removal algorithms, or even what people did manually in psychological studies, were based on individual channels. What we have here is collective information, which was usually not used. Okay, to get things like eye blinks, movements. Here it's moving your eyes sideways, probably, and so on and so on. These are different events that have different characteristics. Now we can look not just on at the largest eigenvalues, but at the spectra. So of course, for the full-time correlation, use some correlation estimator, you get the Martin-Kompastur distribution. Can you actually expect to see that in the neural data? Like, and how many of you would expect to see that? You already know it's not non-Gaussian, you already know it's non-stationary, anything can happen. So is it actually any good type of distribution to compare it to? Well, we do have some better ones, but not really that much. So we have maybe ARMA processes that Steve also was doing. So autoregressive moving array processes. We can have some theoretical, we have some theoretical results on the spectra of those. Maybe we can use, if we assume, as one of our collaborators does, that the brain is like a physical system at a critical point, maybe we can use the spectra from other physical model systems, like Ising model, that are at the critical point, and compare it to that. And so that's the, here you can see that's the Marchenko-Pasteur distribution here, and that's taken from that paper. And these are for critical and sub or overcritical system, Ising systems. So this is markedly different already, just looking at by looking at the eigenspectra. And what do we get from our data? So the data is this orange one. So this orange one here. The blue one is Marchenko-Pasteur. What you get from fitting ARMA processes and getting the theoretical result for that, you get something here. And you can see that the data are not centered on one, as you would like them to be. And again, that's for a good reason. You have some type of market mode, some outlying value, eigenvalue, big one, which makes all the other part of the spectrum to move left. And to get that, you can actually take vector autoregressive processes, which do couple all the channels together, and you can then get some collective mode as well from that, and that's what happens here in the blue line, blue histogram. But it's okay. It gets there a little bit, but it's not perfect. And a thing that you probably can't see is like an invisible histogram here, transparent one. This is the thing that you would get from Ising model, which is again far from what we get. Now this is only experimental data. This is resting state with closed eyes, resting state with open eyes, and a person doing the specific task that you ask them to do. And again, you can see that when you're at rest, when you're not supposedly not doing anything or not thinking about anything specific, that's different than during doing some tasks. So again, maybe there is some larger eigenvalue that corresponds to you processing some specific type of data that moves all the other spectrum to the left. So I'm gonna just give you those observations. That's interpreting all that is I guess much further actually. Then we can just get to lag correlations. So we get the lag. Now the Wojtek and our boss made the result that gives you a way of calculating the radius within which the eigenspectrum of lagged correlation matrices for Gaussian IID and variables would lie. And so of course, this is now asymmetric, so you get the whole imaginary spectrum. So this thing here is the radius of that circle. And it depends on the lag, on the rectangularity of your data. And that's the experimental measurement. But so there is the theoretical result somewhere here, the red circle. Now the colored points are the first eigenvalue. So the blue is first eigenvalue, the yellow is the second largest eigenvalue, and so on. And these are collected when you make the lag larger and larger. So when you time shift it. So first you start at the 0 axis because it's symmetric, and then you go to the imaginary axis. Now you can make it look nicer if you whiten time series. So you get rid of the correlations of all the equal time correlations. You rescale the time series by the similarity transformation that you use to diagonalize the equal time correlations. Now you see a little bit more than here. Now the funny thing is, do you have any bets or guesses why you'd get this structure, circular structure there? This could have any shape, principle. Well, the funny thing is we kind of rediscovered the simplest thing possible that was immediately known after first EEG experiments like 100 years ago, or more, actually more than that. That is the alpharism, which is whenever you have oscillatory signal, you get something that scales like a cosine of the phase differences. So then your eigenvalues also behave like that. And when you just when you just shift the time, just go along that line, that takes 15 milliseconds, that takes another 15 milliseconds, that your 100 milliseconds to 10 hertz that you have from the algorithm. And now, that's the very strong effect. Sadly, it's not interesting for a psychologist because they all know it. You can also look at, so again, that's for raw time series, that's for differentiated time series, and again, differentiated and whitened. So we can see that, basically that's the last observation. We can see that there is some structure that is non-random. The bad thing is we don't know how to interpret it yet. Okay, and just to show you that comparison with the, again, 2D Ising critical model, you get something again different. And the fun thing with the Ising is that you can see that there are a couple of eigenvalues that change places. So this line is kind of that line, but it changes colors. So there are actually several large eigenvalues lying very close to each other, and they just change places every now and then. Okay, that's basically the whole picture of what we have found until now. It is still very much work in progress. So what you've seen is that all the collective information that resides in the neural activity can be seen in the eigenvalues, but more importantly also in the eigenvectors. So we're aiming at getting more interesting information from there. As you have seen on the one of the first slides with the inverse participation ratio plots. So for now, it seems that actually it might be a reasonable way to improve detection and classification of artifacts, and getting, not so much maybe getting rid of them, but at least spotting them. And yeah, the question is still, okay, what type of now model that would be solvable can we find to at least fit the spectral density, and that we do not know. So okay, that's one of the psychologists from our university that helped me with the experiment. These guys you know, that's one of our collaborators from Argentina. It's also neuroscience. Thank you so much.
So it's time for questions.
Is there virtue experimentally in looking at a single EEG track and looking at the autocovariance, the empirical autocovariance spectrum? Have people done that, and is there any interesting signal in that?
I'm not sure. We're kind of doing that with the fMRI signals. So
for that we have a fairly decent finite size, finite sample analysis.
Yes. So I mean, of course, once you have the 1/f noise, you also have all that autocorrelations there. So yeah, we already have some knowledge on that, but getting with that autocorrelations into the collective modes, I have no idea.
If people are doing this research on the dependence of the signals, even between people from different races and so on, would it be also visible in this kind of?
So sometimes it is. So actually, Dante, Kelvin, and Faraday figured out an actually met her at the Zakopane Summer School. Well, they actually have shown that people, not really of different races, but of different economic status or different civilization status, maybe, they might or might not have the algorithms when they have eyes closed, resting state. So actually, some of those rhythms are just individual. There's plenty of individual variability between from person to person, but there's also something going on there that, I mean, this alpha rhythm is very strong. Many people have it, but then people from India, or like very poor people from India that don't have access to all the equipments that we have now, they do not they do not exhibit this type of players. And this was not known just because people were interested in Europeans and Americans. So yeah.
Okay. Any other questions? If not, then let's end the speaker.